So now in this part of the chapter, we're going to start talking about some different types of reactions and specifically how to classify them, and in the case of double displacement, how to predict the products of a certain type of reaction. This double displacement reaction is one where we'll be able to actually, without even seeing it, predict what products are formed, and that's a neat skill to have. So let's look at double displacement. We identify double displacement by having two ionic reactants. How do we know these are ionic? Well, silver is a metal, right? It's made out of silver plus ions. Remember, silver was one of the transition metals that has a fixed charge. So make sure you've got that written on a periodic table somewhere. Silver is plus, and nitrate is a polyatomic ion. It's 1 minus. And here we got sodium plus, and here we got iodide minus. So if it's a metal and a polyatomic ion, or a metal and a nonmetal, those are all ionic compounds. So when we've got two ionic compounds, it is a double displacement reaction. What we need to do is write ion pairs for the reactants. That's what we did right here. We wrote out we separated them into their individual ions with charges. With charges. And then, to make the possible products, what we're going to do is swap the ions, making new plus-minus pairs. Okay? So, silver will be paired with, I'm having trouble drawing this arrow for some reason. Silver will be paired with I'll get it at some point, I promise. Why is this so hard to do? Okay. There! Silver will be paired with the iodide ion. Okay, that's a new ion pair. A way of thinking of this is that when we have silver nitrate and sodium iodide, and when we pour them together, we get all four of these ions floating around in solution. And a possible way of making a product would be if they paired up in a different way. So silver is paired with nitrate originally, but it could be paired with iodide, if we think it that way. The other pairs, it could not be paired with sodium because they're both plus. Ion pairs are always positive, negative. Okay? So then the other pair will start positive, right? Sodium pairing with nitrate. Those are the new ion pairs. And then make formulas for possible products from those new ion pairs. So this ion pair makes silver iodide. This ion pair makes sodium nitrate. Leave room for a coefficient in front, leave room for a phase label behind. It was easy in this case because they're both plus-minus ions. Plus-minus, so we just needed one of each. But as soon as those charges start to change, that makes it all the more important that we use those charges to write the new formulas. If one of these was some different charge or something like that, we would have to write this formula based off of that charge, not necessarily based on what it looked like over here. Okay, that's going to sort of be the key here. Balance if necessary. This one is pretty easy. Silver, we can count nitrate as a group. Sodium, iodide, it's already balanced. But then the new part here is to predict phase labels of those products. Because in order for this reaction to actually be observable, there has to be some sort of change in phase label. Because look at silver nitrate and sodium iodide. They're both aqueous, which means they're both dissolved in water. They'll pretty much just look like water. Clear, colorless solutions. And if we mix them together, if both of these products were also aqueous, it would look like nothing happened. It would look like you just mixed them. But in order to observe a reaction, if one of these had, say, a solid phase label, we would be able to observe that. So take a look at this picture here. This is silver nitrate. what was in here originally was a sodium iodide solution, AQ, AQ. Look how silver nitrate looks like water, sodium iodide looks like water, but here is some sort of new product. That is a solid. The only way that we can see something like that forming is if it is a solid, something that is not dissolved, that actually shows up in there. So some kind of reaction has happened, but it turns out we have a way of actually predicting that without even seeing a picture or without even really doing much of anything. And it requires predicting those phase labels of those products. So we'll come back to this page. Let's go on to rules for solubility of ionic compounds. Turns out that some ionic compounds very easily dissolve in water. Think of something like sodium chloride. If you pour a little sodium chloride in water and stir it, it becomes sodium chloride aqueous. Okay? That is a soluble ionic compound. It is easily able to fully dissolve. Some ionic compounds never dissolve in water. If you imagine something like chalk dust or sand or something like that, no matter how finely you've grounded it up, and no matter how long you stir it, it will just settle right back down to the bottom again. Okay? That is insoluble. Chalk is usually made out of something like calcium carbonate. So it will remain as a solid, no matter how long you stir it, no matter what. Okay? And that just depends on the ionic compound itself. Some easily dissolve in water, some do not. So to figure that out, we have these solubility rules for ionic compounds. Note that this following table will be given on the exam. Okay? It will be provided. I had to clarify that for somebody once. It will be provided for you on the exam, exactly as shown here. Okay. So you don't need to memorize it, but you do need to know how to use it. And, of course, you need to know what nitrate and acetate and sulfate and bromide, and so you still need to know what those things are. Okay? But this is just telling you how those substances behave when they're dissolved, or when they're how they behave with water, if they dissolve or not. So there's sort of two parts to this table. The first part here, the top half is the fact that most compounds containing the following ions are soluble. Okay? So let's start out with the first row. Lithium, sodium, potassium, ammonium, and also nitrate and acetate. Whenever any of those ions show up, the ionic compound is soluble, meaning it will fully dissolve. And if it fully dissolves, what phase label does it get? What's the phase label for things that have been dissolved? It's AQ. So write an AQ over here. So all you have to identify is any one of these ions within your compound that makes the compound soluble. Okay? This does not mean that individual lithium is soluble or something like that. This is talking about when these are part of a compound, that those individual ions make them soluble. Okay? Same goes pretty much for chloride, bromide, iodide, okay? Except now there are exceptions. So what you have to do, if you have a compound that has chloride in it, for instance, look over to the right to see if the other ion in that compound turns it into an exception or not. Okay? So most compounds containing chloride, bromide, and iodide make the compound soluble. Okay? Most compounds are soluble that contain chloride, bromide, and iodide. But, look over here, when any of those three ions pairs with silver, mercury, or lead, the compound is insoluble. And when something is insoluble, that is a solid phase label. So don't get confused with the S. S does not mean soluble. S means solid. That is a phase label. When something is insoluble, that means it does not dissolve. It stays as a solid. Okay? So same thing happens with sulfate. Most sulfate compounds are soluble, but there are exceptions. When sulfate pairs with strontium, barium, lead, or calcium, the compound is insoluble. Okay? Now, the bottom half of this table is opposite. These ions, right here, make most of their compounds therein insoluble, which are solids, but you have to look for exceptions. Now, these three sets of exceptions go for both of those. Okay, hydroxide and sulfide, okay, have exceptions here. If most compounds are insoluble, but these are the exceptions are now aqueous. Okay, so these ones are just sulfide, these ones are hydroxide, but be a little bit careful with this. When hydroxide pairs with calcium, strontium, or barium, the compound is slightly soluble, but for many purposes, they may be considered insoluble. And for our purposes in this class, we're going to consider these ones still to be insoluble. We have to put that there for a couple of reasons. We might talk later on about that. But for instance, hydroxide paired with calcium, we're going to call that insoluble for now. Okay. So, for instance, sodium phosphate. All you have to do is identify what ions are in this, the sodium ion, the phosphate ion, and look in this, sort of start from the top, look on this, and identify one of those ions. Okay? We would see sodium right here. And when sodium is in a compound, the compound is soluble, and there are no exceptions to that. So that's AQ. If you want to write soluble, you can. Soluble and AQ. But really what we're looking for is that phase label. Okay? If by chance you happen to see this phosphate first, that's fine, it still works. Most phosphate compounds are insoluble, but then you got to be careful. Over here, when we've paired sodium with it, the compound is actually soluble. Okay? So these exceptions here are actually the same rule as what's up on the top. So there are no conflicts on this table. Okay? Doesn't matter. You just have to find one of your ions over here and then check to see if the other ion makes it a exception or not. Calcium phosphate, Ca3PO4 so no calcium. There's phosphate though. There's phosphate. Phosphates are insoluble. If it's paired with lithium, sodium, or potassium, it would be opposite, but that's not. So this is insoluble, which is a solid phase label. Okay, so why don't you pause me again, why don't you see if you can fill out phase labels for the rest of these using those solubility rules. Again, just identifying one of the ions over here, then seeing if the other ion makes it an exception or not. Calcium iodide, here's iodide. Calcium is not an exception, so AQ. PbI2, that's lead 2 iodide. Here's iodide, but there's lead 2 right there, so it's an exception. It is solid. Iron 3 hydroxide. Here's hydroxides. See nothing about iron over here, so solid. Here's calcium hydroxide. Oh, and hydroxide pairs with calcium. It's slightly soluble, but for many purposes, we're going to consider that insoluble. Potassium carbonate. Very first rule, anything with potassium, AQ. Copper. I bet you might want to call that copper carbonate, right? But that's not quite right. Copper is variable charge, so it needs a Roman numeral. What's its Roman numeral? What's carbonate's charge? It's 2 minus. So this copper is a 2 plus. This is copper 2 carbonate. If you haven't quite practiced all of your naming and formula and stuff, you would have gotten that one wrong. So careful about that. Anyway, carbonate over here. Carbonates are insoluble. Copper is not an exception, so solid. Okay. So again, you don't need to memorize these. Solubility rules will be provided for you. You need to know how to use this table. You need to know what these ions are, whose names are given here. We can go back one page and use this in our example, though, to predict the phase labels of these two products. Here's silver iodide, AgI. Let's look at our solubility rules. What is it? What is it? Here's iodide. Iodides are AQ, but here's silver. Silver makes an exception. Okay, right? When iodide pairs with silver, that is a solid. Sodium, anything sodium is AQ. Okay, so what is the identity of this yellow solid that's formed in here? Based on the phase labels we predicted, that is the silver iodide that is formed. So that's a solid that is formed. It'll look like this sort of plume of something that you can no longer see through. Eventually, that will settle to the bottom, and you could filter it out, I suppose.